Let me use one more analogy. You know what the photoelectric effect is? Photoelectric effect is using photons to knock electrons off matter. If I try to use red light to knock a photon off matter, it's not going to be very effective because each photon doesn't pack much punch. Whereas if I use X-rays to try to knock off electrons, I'm going to be successful because X-rays are ionizing radiation. Well, some pieces of matter are easy to knock electrons off. What kind of matter do you think is the easiest to knock electrons off of? Metals, right? And the metals, what? Alkali metals, alkaline earth metals, transition metals, lanthanide, actinide. Alkali metals are going to be the easiest. So the photoelectric effect historically has been with alkali metals, like potassium. If I look at potassium metal is so easy to knock electrons off. Visible light can knock electrons off. But not just any visible light. For example, if I shine blue light on this, and so let's say I have 100 watts of blue light. If I have 100 watts of blue light, that can knock an electron off potassium. And so for potassium, what you want to do is you want to store potassium in a light-proof container. A light-proof container would be like a brown bottle or amber bottle, something that light can't get in and start to decompose your potassium by ionizing it, right? Forming other stuff. So if I try to do the same thing with 100 watts of red light's going to have a longer wavelength, right? But it's going to have the same total energy, 100 watts of red. We'll know that, or it turns out that the 100 watts of red light is not enough to knock an electron off. And it's just because of the red photons are not quite as energetic as the blue photons. But what if I do this? Actually, blue, should I make them bigger or smaller? Well, just fewer, but maybe smaller, like this. And so a lot of energy concentrated in a small packet. How about that? Whereas I'm going to bump up the total power of the red light. Let's go to 1,000 watts. If I went to 1,000 watts of red, surely that must be able to knock electrons off. Wouldn't you think? If I went to 1,000 watts of red. It's not enough. If I went to 1,000 watts of red, does it change the wavelength? No. Does it change the frequency? No. It doesn't. The wavelength is the same. The frequency is going to be the same. Because does it change the speed? No. What does it change? It changes the amplitude. And so if I went to 1,000 watts, I have a tidal wave of these red photons coming down. And so if I have a tidal wave of these red photons coming at the same, so let's go with 1,000 watts here. And so it's just huge amplitude, huge wave. Is it going to knock electrons off? 1,000 watts? No. No, it doesn't. And so nothing happens here. Whereas if I went to 1,000 watts of blue, do you know what's going to happen? You're going to inject a lot of electrons. A lot of electrons. Because I'm going to have a lot more blue photons hitting it.
If we're talking about photo energy, would be like 1,000, if they were both delivering 100 watts, would they deliver it faster than the red light? Or?
No. It's just, they're going to deliver it the same because it's 100 joules per second. But the situation is, in a way it delivers it, I guess, faster in the sense that each blue photon packs a lot more energy. And so the energy transfer for an individual photon is going to be more significant. But at the same time, it's got to be 100 joules per second energy throughput. And so therefore, for every one of these, at the same time, you have a bunch of these hitting. And so we're going to get the same energy transfer. It's just the energy transfer how it's distributed. And so what this boils down to is something called quantum stoichiometry. When we look at quantum stoichiometry, let's say, if one blue photon knocks an electron off, then surely if I have 10 red photons simultaneously hitting this, shouldn't it do it? Because 10 red photons can pack the same punch, right? Or something like that. And so it turns out that no, it doesn't, because let's say, one electron ejected plus one photon. In other words, one electron plus one photon, oops, this is wrong, sorry. One electron plus one photon equals one electron ejected. Well, if I know the energy of that photon, that packet of energy, the packet of light that can eject that, then maybe I can do this. One electron plus two photons of equivalent energy, total energy, should be able to eject it, right? Plus two photons of lower energy, but these two photons equal the same energy as this. Will this be able to do it? No. And so this is, well, what if I have a super photon? Let's get a photon that's twice as energetic as this. If I have a photon that's twice as energetic as this, will it eject two electrons rather than one electron? No, it won't. You can't knock out two electrons, even if it's twice as energetic. All it's going to do is it's going to knock one electron off, and it's going to kick it off with high speed. That's all. And so this is quantum stoichiometry. It's a 1-to-1 ratio or 1-to-1 mole ratio. If I need to eject a mole of electrons, I need a mole of photons. And so this is the photoelectric effect here. And so let's do an application of the photoelectric effect. Well, one application are light sensors. When you're ejecting electrons, you generate a current. And so if you block the light, it stops the current, and then it can signal something, right? And it's in a tube. And you got to protect the potassium metal from oxidation. So you might see these photoelectric sensors. That's one application. Another application is just in calculation. So let's do a calculation of this kind of thing. But we don't have to eject electrons. We could cause other damage to occur. So for example, a carbon-carbon bond, like in DNA. DNA is, you have some carbon-carbon single bonds in there. And a carbon-carbon bond takes 347 kilojoules per mole of energy to break. And so we know how much energy it costs to break this. There are different ways to break the bond. You could heat it up, you could use electric discharge, or you could use light, right? You probably can already guess what type of light do you need to break bonds? Gamma rays and X-rays will break bonds. UV, right? UV is typically used to break bonds. Well, let's see. Let's see how strong this is. Do we need gamma rays or X-rays, or will UV break this? Or maybe even violet. Will violet light break this? And so what we're going to do is we're just going to ask, what is the minimum energy? Minimum energy. What is the minimum energy? Well, the minimum energy required to break is already given, right? Minimum energy is 347 kilojoules. If you don't have 347 kilojoules, are you going to break it? No. So we know the minimum energy. What is the minimum energy? But if we want to use light, then light can be characterized by energy or frequency, And so if I ask what is the minimum energy, that's like asking what is the minimum frequency? What is the minimum energy, minimum frequency, And so if you have a lower frequency, then it might not be enough punch to break that bond. So minimum frequency, and any frequency higher should have even more punch to it. But when we're talking about minimum energy, minimum frequency, when we're related to wavelength, what do we have to do for wavelength? We have to, it's inversely proportional. And so we wouldn't say minimum wavelength, we would say maximum wavelength. maximum. That is, if you go to an even longer wavelength, it's not going to be enough. And so this is the max you could go. Shorter wavelengths, no problem. But longer wavelengths, trouble. And so what is the minimum energy, minimum frequency, maximum wavelength of light required to break this? Bond. So, we look at our equations we come up with. Now, what is the equation for the energy of light? Well, the energy of light, I should have done this earlier, but I forgot to write this equation here. The energy of the photon of light is given by its frequency times h. H is called Planck's constant. Planck's constant is equal to 6.626 times 10 to the minus 34 joules times seconds. Joules times seconds is a unit of action, but you don't have to know that. This is just the frequency. And so if it's equal to h nu, then we know it's also equal to hc over lambda, because frequency is just c over lambda. And so we know lambda, at least we know two wavelengths of light. What are the two wavelengths of light that you know? Let's start off with lambda. Lambda is equal to hc over the energy. You know 760 nanometers at the edge of red and 390 nanometers at the edge of and so let's see, hc over E, H is 6.626 times 10 to the minus 34 joules times seconds. C, we're going to use 3 sig figs, 3.00 times 10 to the 8 meters per second, or you could use 4, 2.998 times 10 to the 8 meters per second, over E, which is 6, E was 347 kilojoules. 347 kilojoules, we got to get rid of kilojoules, convert that to joules, so this is 1,000 joules per kilojoule. So the unit should work out to meters.
So do we have to know the constant? That constant that we use?
Do you have to memorize it? No. You don't have to memorize it.
So it's going to be given to us?
Yes, it's going to be given to you.
Right. Where do you get the 3 times 10?
That's also given to you. That's the speed of light. C. C is the speed of light. And you don't have to have that memorized. And so this is given. This is given. All right, so let's do the calculations here. So 6.626, unless somebody already has a calculator. Does somebody have a calculator? 6.626, come on. Let's have this on rotation law. Yes, do. 6.626 times 10 to the minus 34. You know, 34 negative.
Yeah.
Times 3 times 10 to the 8th. Divided by 0.347. Equals, I get 5.728 times 10 to the minus 25 meters.
I think it's minus 31.
Divided by 300,000.
Oh, you're right. Times 10, minus 31.6, I'm on. Times 10 to the minus 31 meters. Is that what you guys got? And so what kind of light is that? Well, you know, what do wavelengths range from? Wavelengths range from smaller than an atom to kilometers, right? And so I look on the chart, this is like page 246 or something like that. You look on the chart and you see gamma rays. Gamma rays are going to have the shortest wavelength, right? And so the edge of the gamma rays is around 10 to the minus 15 meters, 10 to the minus 16 meters. And so we're way out here at 10 to the minus 31 meters. 10 to the minus 31 meters. 10 to the minus 31 meters is what kind of light? Well, that's much higher energy than gamma rays. So what is much, much higher energy than gamma rays? Super gamma rays? Cosmic rays?
Is it even attainable?
No. This is an insane amount of energy. It's this is why your chart ends at 10 to the minus 15 to the minus 16 because
So the answer is not true.
but 10 to the minus 31. 10 to the minus 31 meters. Well, what is it?
Doesn't exist.
No, we're not going to have that. In fact, there was an error in our calculation. What was the error in our calculation? Our error in the calculations, we have to be careful about energies. And this, for light, we have to think, because in chapter 7, everything was like per gram or per mole, right? But in light, we often work with per atom, per carbon-carbon bond, single atom. So we have to get comfortable with two different quantities of energy. 347 kilojoules of energy packed into a single carbon-carbon bond would do what? Sure, it would break the bond, but it also break everything else. The carbon atoms, the nuclei, everything would be destroyed, basically, because the amount of energy is huge for, just for one carbon-carbon bond and two atoms, right? And so we have to be careful because, there was some unit that I wasn't very careful with, and lots of students aren't very careful with, and that is 347 kilojoules per mole. Not 347 kilojoules per bond. And so we got to watch out for this. What we need to do is we need to figure out how many kilojoules are required per bond. And so it turns out that for mole bonds, there are 6.022 times 10 to the 23rd bonds. And so now we can figure out the energy required for a single bond. Can somebody punch this out? Or I'll try. I don't really like this calculator so much. 347 divided by Avogadro's number, 6.022 times 10 to the 23rd equals 5.762 times 10 to the minus 22 kilojoules per bond. Do you see the total? How much water can you heat up? How much water can you heat up with 5.76 times 10 to the minus 22 kilojoules? If you put 5.762 times 10 to the minus 22 kilojoules into a cup of water, what's the temperature change? Can you even measure? You can't even measure the temperature change. If you put that much energy into nothing's going to happen, right? Nothing. But if you put that much energy into a single carbon-carbon bond, what's going to happen? It'll break. And so we have always we look at two energies. We're looking at the energies per mole, and we're looking at the
Energies per bond or molecule.
per bond, per atom, per photon. When we're dealing with the energy per bond, atom, molecule, photon, the scale is extremely small, 10 to the minus 20, 21, 10 to the minus 22, 10 to the minus 23 joules. That's a tremendous amount of energy. But when we're looking at it per mole, like a mole of water, 18 grams of water, then we want, joules or kilojoules worth of energy to go into that. And so now we can do this. Now let's repeat the calculation. Lambda is equal to hc over the energy, the photon. So recalculating this, I'm going to flip this calculator times h 6.626 times 10 to the minus 34 times c 3 times 10 to the 8. And I get this. I get 3.44 times 10 to the minus 7 meters. What kind of light is that? 3.44 times 10 to the minus 7. Well, we know nanometers. And so do you know a nanometer is nano is 10 to the minus, micro is 10 to the minus 6.
Yeah, 10 to the minus 9.
Yeah. And so let's get this to 10 to the minus 9. So it would be 344 times 10 to the minus 9 meters, which is 344 nanometers, which is UV. And so, 390 is the edge of violet, right? We don't have to go very deep into the UV to start breaking carbon-carbon bonds. Correct? This is old data. I should probably look up the new data because of ozone depletion. But basically, the old data was many years ago. They determined that every day when you go outside, you get exposed to UV radiation from the sun, right? And every day your DNA gets cleaved. That is, the UV radiation breaks the carbon-carbon bond or whatever else bonds, what other bonds you have, 200 times. So 200 times a day, your DNA is being broken. That's some serious damage, right? But biology is a pretty amazing thing because there are repair enzymes that go in and repair the damage. Have you heard that? Yeah. So repair enzymes can, and so it doesn't cause permanent damage, likely. So you're accustomed to that. And so it doesn't take much UV to do that. So this is an example of the thing. Now, what people will say is that because of photons, that means light is quantized, right? Light is quantized. And what did I say about quantized? That light is quantized. Quantized means that there are allowed and forbidden energies, right? And so if light is quantized, what are the forbidden energies of light? Tell me. If light is quantized, what is forbidden? Because remember, quantized means it occurs in steps, and between the steps is forbidden. And so you could go step 1 to step 2, but anything 1.1, 1.2 is forbidden. And so I need to know what is the forbidden part. What kind of light is forbidden? Because it comes in packets. Anything past gamma rays is forbidden? Okay, anybody else? Well, anything past gamma rays, but that means everything below gamma rays is continuous and anything past gamma rays is forbidden? Is that what it means? Because you guys know the difference between continuous and quantized, right? Continuous and quantized. And so if light is quantized, then that means it occurs in steps. And so one of the steps, maybe it's like this. As light is quantized, it means that you jump from red to orange, and anything between red and orange is forbidden. Is that what it means? There's a gap here of forbidden energies. No. Are all the colors in the rainbow allowed? Well, for example, any shade of red I want from 760 to, where does red end? I don't know. Could I have a shade of red that's 759.238 nanometers. Is that allowed? Could I have a shade of red that is 759.237 nanometers? Is that allowed or forbidden? That's allowed. And could I have anything in between those? Yes. Because all the colors of the rainbow forms a continuous rainbow. When you look at a rainbow, you don't see black streaks through there, right? Saying, oh, between these two colors it's forbidden. There's no gaps. And so when we look at a rainbow is continuous. This is wrong. It goes red, orange, yellow, green, blue, indigo, violet. This is going in terms of decreasing lambda or increasing energy or frequency. Right? Violet being the highest energy. Now, light is quantized means, it doesn't mean this. This is continuous. In fact, the electromagnetic spectrum is continuous. And so let's just say, in fact, the entire electromagnetic spectrum, electromagnetic, I'm just going to abbreviate EM. The entire EM spectrum is continuous. And so what is quantized?
Whatever's outside of it?
No, not exactly. Not what's outside of it. You have to think about this.
Is it a fact? Is it true?
Isn't it like
Oh, that,
everything quantized is like,
you have an answer?
Is it the true statement? Is a fact?
In fact, the entire electromagnetic spectrum is continuous. This is a true statement. There's no color of the rainbow that's missing. Correct? And the steps can be infinitesimally small. You know, because this ranges from 760 nanometers to 390 nanometers. And it's not in 1 nanometer increments. It doesn't go 760, gap, 761, gap, 762, right? It just is a continuous rainbow of colors. And you can pinpoint any color of light and determine its wavelength to extremely high precision, lots of sig figs. Right? And so, this is very,
The energy in the photon.
yeah. What's quantized is this. You can have any size of photon. Which one is the biggest photon? The most energetic photon, would you say? Violet. Violet is, what do you want to do for big energy for a photon? A small photon or a big photon? Small, okay. In terms of dense, let's say it's highly dense, packs a lot of punch. And so we put all that in there. And red photon will make big, like less dense, right? It's fluffy. So this is kind of red. Can we have any size photon? Yes. Any size photon. The size of the photons forms a continuum. And so all sizes are allowed. All sizes of photons are allowed. And so we could make a little smaller photon, a little smaller, until we get to violet, and then beyond in the opposite way, right?
so red would be the largest photons and then once you get to violet.
Well, the least energetic. Least energetic.
So in general, like red can't have a small photon? Or,
No, there could be red photons that are smaller.
oh,
The range of red photons ranges from this kind of large fluffy one to more dense, it'll pack more punch. We're throwing these photons at the same speed, let's say. And so to try to visualize the energies, if you get hit by these photons at the speed of light, which one's going to hurt the most? The ones that are really dense with energy, or the ones that are kind of not very dense with energy? Yeah, the ones with dense with energy. So we can have, but we have any size, any size here is allowed, right? And so if any size is allowed, that's called a continuum. And so we have a continuum of allowed energies. So what is quantized? Seems like nothing's quantized because we have a continuum of photon energies.
Is it all sizes of photons or all energy?
All sizes. All sizes and all energies of photons. All sizes and energies of photons. I don't know how big a photon is. When I say sizes, I meant energy.
Well, like,
Because you can't have.
wouldn't you consider the sun continuous?
The sun is continuous. It gives you continuous rainbow colors, doesn't it?
So
White light.
anything that doesn't have, like, that's not allowed forbidden lights to be quantized?
Yeah, the question is, what is forbidden? And so if it's continuum, then nothing's forbidden. Continuum, by definition, means nothing's forbidden. All of them are allowed, right? All the colors are allowed, aren't they, in the rainbow? There's no forbidden colors in the rainbow. That's clear. And so when somebody says light is quantized, what the heck are they talking about? Light is not quantized. Light is a continuum. We go from gamma rays all the way to TV radio. All those are allowed. There's nothing forbidden.
Individual photons, there can't be half a photon.
Yes, right. So what is, why it's quantized is, let's pick 760 nanometer red. 760 nanometer red consists of this size photon. This is the lowest energy possible. The lowest energy is equal to h nu, right? Now, let's say I want to increase the energy a little bit. If I want to increase the energy a little bit, then I have to pick either a shorter wavelength red, then I can increase the energy a little bit. Or, let's say I just want to stick with 760. What's the next energy that's allowed? The next energy that's allowed is 2h nu. That is, 2 of these big photons. But I don't want 2h nu. I want 1.5h nu. Is 1.5h nu at 760 allowed? No, that's forbidden. And so energy is quantized in the sense of the photon energy. That is, I can have E equals n times h nu, where n is 1, 2, 3, etc., but nothing in between. And so here is where energy is quantized. There's any size ball I want, but once I stick with one size ball, then it's quantized because, to get to the next energy, I have to double or triple or n times. But I can't go a fraction higher. That doesn't mean, let's say if I wanted something equivalent to h nu, 1.5 h nu, then I just pick a different photon, slightly energetic photon, that it have that energy. And so it's quantized in the sense that when you look at a specific wavelength, a specific packet, then it's quantized in this way. Does that make sense? All right. And so this, we keep track of these types of things. And so let's take a look at the hydrogen atom spectrum. So these are the properties of light. We want to understand the two energies. The photon energy and the total energy.
Does n represent like number of protons?
Number of photons.
Right.
N is the number.
You cannot have like such like 1.5 protons.
1.5 what?
You cannot have like 1.5 protons.
1.5, I'm sorry, what's that? 1.5 what?
You said
Photons?
Yeah.
No, you cannot have 1.5 photons here. But you could have, you could have this energy. You could have this energy, 1.58. This energy is allowed, but not with this photon. This energy, all energies are allowed. You know that? There are no forbidden energies. All energies are allowed. But if you tried to make this energy with using these photons, let's say I just have quarters. I have quarters, but that item's 58 cents. you know? Well, 58 cents, are you allowed to make 58 cents with only quarters? That's forbidden, it's quantized, do you see? But is 58 cents allowed? Sure, you know, it's a continuum, right? And so this is the same thing. I just have quarters. I can't get this $1.50. Well, I can get $1.50 with quarters. I have dollar bills. I have dollar bills, and it's a $1.50 item. Can I get a $1.50 item with dollar bills? No, but sure, I could use a different photon. I could use a $1.50 photon, right? And so all energies are allowed, but how you build those energies, you know, this is the total energy. All energies are allowed. There's a continuum of energies. There's no forbidden energies. But depending on what you're doing here, it might be forbidden or it might be allowed, you know, with the photons. That's it. And so, okay, now we're going to go back to the quantum development, you know, where we talked about observation and then pattern and then law and then hypotheses and then theory. So let's continue this discussion. The pattern, the unusual light pattern. We're going to go to the hydrogen atom spectrum in the visible. In the hydrogen atom spectrum, let's take a look, and you guys took the measurements, but I'm going to just use the ones in the book here. Okay, we're going to go in terms of wavelength. So increasing lambda here. So this is red, this is violet, and then we'll just fill it Roy, G, bid. And it turns out that the hydrogen electron absorbs a red photon at 656.3 nanometers. And so at 656.3 nanometers, we have a line that corresponds to, this is emission. And so we're looking at the emission intensity here, I. And so it emits a red photon at that, and then there's a green photon at 46.1, blue-green photon, 46.1 nanometers. And then there is a blue photon at 434.0. 434.0. Actually, the red is the most intense. 434.0. And then finally there's a violet photon at 410.1 nanometers. This one's not very intense, 410.1. Okay, so what we see are 4 allowed energies. These are allowed. And everything else is forbidden. So any other color of red is forbidden, all of orange, all of yellow, most of green, a couple of blue, green, blue, and some violet. This is all forbidden. Is an electron forbidden from taking those? If you have an electron in free space, let's say an electron in a vacuum, can an electron in the vacuum move at any speed it wants? You know, as long as you accelerate it? Can it move at any speed, or are there forbidden speeds for an electron moving? Let's say there's an electron moving across this room. Are there forbidden speeds for the electron? No. I mean, what would forbid the speed? You know, the electron's just moving like this, right? And so an electron, this is already known, an electron in free space, the energy of an electron in free space is continuous. It can move at any speed it wants. But when that electron gets placed in an atom, then all of a sudden it becomes quantized. Yeah. But wait a minute. How about an electron in a light bulb? How about an electron in an incandescent light bulb? Can that move at any speed it wants? Or can it vibrate at any frequency it wants or oscillate at any frequency it wants? Yeah, the answer is yes. If you have a tungsten filament in an incandescent light bulb, that tungsten filament is going to excite electrons when we pass electric current through there because there's resistance and a little heat. But anyway, the electrons can vibrate or oscillate like a red, orange, yellow, green. You know, there's no vibration that's forbidden. And so as it vibrates like this at green, let's say, eventually it's going to calm down. When it calms down, energy is conserved, it's got to release that energy as this light in this case because it's pretty high energy. So green photons emitted. But can that electron in tungsten metal vibrate at red? Yeah. Orange? Yeah. All of these. When you looked at the emission spectrum from the tungsten light bulb, was it continuous or were there black gaps? Or not black gaps, but were there gaps in the peaks? It was continuous. And so what that means is that an electron in free space, an electron in tungsten metal, has a continuum of energies allowed. Sure, you know, even having a continuum of energies allowed, light is still quantized in the sense that, you know, it comes in different sized photons, right? But we ignore that because it's just a continuous rainbow of colors. Now this is quantized at a different level. And so here, when we look at the rainbow, yeah, it's continuous, but quantized here. This is quantized in a different sense because, yes, we still are quantized this way because a blue photon comes in specific sizes, right? But this is going to be quantized in another sense. This is quantized in the sense that, wow, there's a whole bunch of forbidden regions here. That means an electron in a hydrogen atom. A hydrogen atom has just a proton and an electron. And an electron and hydrogen atom can oscillate at this wavelength or frequency. And if I try to get it to oscillate just a little bit faster, just a hair faster, is it possible to get that electron to oscillate a hair faster? No, because it's forbidden. And so it's weird because it oscillates at this, and then I have to jump all the way to here. And now it's oscillating faster, but let's say I want to slow it down a little bit. Is it possible? No, if I want to slow it down, it's got to go back to here. Now it's slow. And so this is weird because all you got is a proton and an electron. Why can't the electron oscillate at any frequency it wants? You know, because it's being decided by light. Light is this wave, right? Oscillating field. So wave comes along, plus minus, right? Wave comes along. I have a wave here, orange. Orange wave comes along, plus minus, electrons here, plus minus, right? Orange wave. It's like you're sitting in a little boat, right? Out on the ocean, and an orange wave comes along, you're going to start oscillating like this, right? This would be like a boat. It's sitting in the ocean. A red wave comes along. Ooh, you start moving with the wave, right? Little boat. And then a little higher energy red comes along, but it's forbidden. You can't oscillate. And then finally an orange wave comes along, more intense, and you start oscillating again. And so what's preventing the electron from oscillating? Isn't the electron just like a boat in water? Can't it just oscillate with the waves that come along? You know? And so this is why it's an unusual light pattern. So the whole thing about an unusual light pattern is, sure, of course it should be able to oscillate any frequency it wants because it's just an electron in space, you know, next to a proton. Of course, it's kind of held close to the proton, but still an electron in space. So electron in space, what's preventing it? You know, there could be an anchor, you know, for example, if you anchor your boat so it can't oscillate up and down with a solid rod or something like that. And then release the anchor here, anchor it, release the anchor, anchor it. But is there an anchor preventing the electron from oscillating with the field? That's a very unusual light pattern on that. And so this was unusual. In this sense, this quantized is not unusual, you know, this photoelectric effect quantized, right? This quantized is weird. Just plain weird. Okay, and so there, and then there's one more thing. You know, if you continue exciting the electron, then what should happen? If you continue exciting the electron, it should start emitting in the UV. Now, tungsten's behaving properly because an electron in a tungsten filament in a light bulb is oscillating any frequency it wants, red, orange, yellow, green, right? Because you get the whole rainbow of colors. Now, if you excite that tungsten higher, we should start seeing UV, and a certain amount of UV. But what's predicted from exciting the electron is not what's observed. And so even tungsten, which was a pretty good black body, was a black body. Black bodies are how things should behave. You know, an electron should be able to oscillate at any frequency and emit, absorb and emit. But even a good black body like tungsten failed. It didn't fail in the visible, pretty much. It failed in the UV. And so even a black bodies you predict excitement in the UV, emission in the UV, but what was observed wasn't exactly what they were predicting. And so they labeled that the UV catastrophe. UV catastrophe. So two unusual light patterns. One, these big forbidden gaps, and two, even for a nice black body, which they thought they had figured out because electron's pretty free in tungsten, can oscillate with the motions of the field or whatever. Even for something as nice as tungsten, it failed. And so those are the two unusual light patterns. The UV catastrophe and this quantized spectrum here are unusual. What was a black body emitter again? It absorbs and emits all colors. And so you'd expect it to absorb UV and emit UV, no problem with that. We have the UV catastrophe, which, I'm not going to get into details. It's just, these were the two unusual light patterns. So what had to happen was a hypothesis came up. And, well, actually, before the hypothesis, what came up? What came up? A law. And so, you know what? All a law is typically is what? A mathematical description of the pattern. And so the law that came from the hydrogen atom was this. It's called the Rydberg law, or the Rydberg equation. I'll call it the Rydberg law since I want to stay consistent with my Rydberg law. Rydberg law just says this, that the energy of the photon fits a pattern. You know, the energy of the photon, as you recall, is just going to be hc over lambda. C over lambda. The energy, and so we see the lambdas over there, and so the energy of the photon turned out to be a constant times 1 over n final squared minus 1 over n initial squared. This is it. And so this constant is called the Rydberg constant. So let me give it to you, or what the constant is. And there are different forms of this depending on if we're looking at the energy, frequency, or the wavelength. So let me find the Rydberg constant here. Well, the Rydberg constant is going to be a positive number, and so when energy is released, should it be a negative number or a positive number? So let me do this. We're going to call this constant this. We're going to call it minus r sub h for And the minus sign is the same thing. You know, if this whole thing comes out negative, then that means energy or photons emitted, or if it's positive, the whole thing comes out positive, it's absorbed. And so R sub H itself is equal to 2.17. This is a number you don't have to memorize. 2.179 times 10 to the minus 18 joule. 2.179 times 10 to the minus 18 joules. And so this mathematical equation fits a pattern where n is equal to 1, 2, 3. So this is quantization. Because is 1.1 allowed? No, it's forbidden. It doesn't match the pattern. And so this is just a mathematical equation. With laws, you know, we don't really have to understand the theory to make predictions with laws, right? Because it fits as expected behavior. You know, and so, for example, the ideal gas law allows you to predict the volume of a gas under certain conditions, right? But do you really have to know much about the theory of gases to do that? No. You just use the law. And so we could use the law to do different things here. Well, for example, we could use the law to figure out what these numbers are. For example, this is n question mark to n question mark. What is n final? What is n initial? Final, initial. That's not too difficult. Actually, do you want to do a calculation like that, or?
Yeah, get a text.
Actually, I want to skip some stuff. But anyway, is this a mathematical fact? This equation?
Yeah.
Yeah, if it fits the data, then yeah, it's a mathematical fact. Do we understand the theory underlying that? Do you have to? No. So, but we can use it. So let's go ahead and use it.
Wait, so we're responsible for that formula or not?
Do you have to memorize that formula? No. You don't have to memorize it. So, for example, lambda equals 656.3 nanometers. What is n final? What is n initial?
What is that the number of photons?
What is n? N is just a number. You know, this number has mathematical restrictions. If you're doing exactly what we do in the next step. What is the next step in the scientific method? You hypothesize. Right now, I don't want to hypothesize. I just want to take this. If n, you know, if n is not an integer 1 and higher, it doesn't fit the pattern. It just so happened mathematically, that's it. All n is just an adjustable variable that they use for the formula to fit the pattern that's observed in the hydrogen spectrum. Who knows what it is at this point? We don't care what it is. We just want to know, does it fit the pattern, and can we make other predictions, right?
Don't you have to give us the energy of a...
Well, I do in a way, because the energy is related to its wavelength here. And so the energy is just going to equal hc over lambda. hc over lambda. But I do the hc over the lambda, and then set this equals minus r sub h, 1 over n final squared minus 1 over n initial squared. But I have a problem here. What is the problem? Two unknowns. And I only have one equation. And so if I have two unknowns in one equation, I'm not going to be able to solve it, or am I?
Well, you're testing for a certain wavelength.
Yeah. And so I know the wavelength, I know h and c, I know r sub h, but I have two unknowns. Usually two unknowns in one equation is not, you can't solve it to a unique, right, solution. You might have multiple answers for this. But in this case, we could get a unique solution because of the restriction on n. So because of the restriction on n, we start to guess what it is. And so after doing a bit of guessing what it is, we see this. We see that n final equals 2 and n initial equals 3. A bit of guessing.
Wait, how do we guess? How do we guess?
Well, you try this. You try 1 and 1. It doesn't work. You try 1 and 2. Doesn't work. 1 and 3. 1, etc., etc. 1 in 999,000, you know. But the thing is,
When we're guessing, what are we looking for? Like, how do we
you remember the method of successive approximations? Are you getting hotter or are you getting colder?
So to what value are we converting
Well, we
to?
started like 1, 2, 3, right?
Like, yeah, like what value are we converting?
We know HC over lambda.
Okay, let me tell you what value you're comparing it to. You're comparing it to minus hc over lambda r sub h is equal to 1 over n final squared minus 1 over n initial squared. So you calculate this number, right? And you look, are you getting hotter or are you getting colder?
Okay.
And so what you do is you start plugging in numbers. Let me tell you, the first set of numbers you plug in, let's say n initials 1, n finals 2, you'll see you're the wrong sign. This sign and this sign aren't going to match. And so you go, okay, I'm going to flip it to change the sign. And so you go 2 and 1. Well, 2 and 1 is too big. It's too big. I got to go to smaller. Well, how can you go smaller? It's 2 to 1. Right. And so if you go 3 to 1, it becomes even bigger. But then you say, well, maybe I don't do that. Maybe I go 3, because this is it. 3 squared is what? 9. And 2 squared is 4. Versus 1 squared is 1, and 2 squared is 4. So the difference between 1/4 and 1 is that big compared to the difference between 1/9 and 1/4? Yes. And you see, the larger these numbers are, the smaller the gap between them is. And so you start playing around with the numbers, and eventually you could get it quite rapidly. You could solve two unknowns in one equation very rapidly to see that. And try it. You'll see that the only thing that's going to work is 3, 2, 2, because if you try anything else, it's either way too small or way too big. And so this is an example of successive approximations to guess the answer when we don't have a second equation. This is just an empirical formula. And so it turns out that this line is n equals 3 to n equals 2. That's my final, this is my initial. The next line is n equals 4 to n equals 2. The next line is n equals 5 to n equals 2. That's just a mathematical pattern. All right. So are we good with that? Or not?
So
the test would give us easier numbers, not like easy numbers to guess, right?
The test, yeah. Actually, these are easy numbers to get, these two.
So I think generally easy to guess.
So, well, the test would look more like this. I probably wouldn't ask you to guess. You know, what we do is we just see these. These are allowed. These are allowed energy. The allowed energies are this. The energy of the photon is going to equal minus r sub h over 1 n final squared minus 1 over n initial squared. And so we do this. If we go from n equals 1 to n equals 2, you know, if we go to n equals 1 to n equals 1, what is the Zero, right? It's not allowed. If we go from n equals 1 to n equals 2, you know, and we calculate the energy of the photon, you know what that is? That photon turns out it's in the UV. There's a specific energy of photon allowed in the UV. So if we actually measured it out here, we'd see that we should see a photon out here in the UV. Can we see it with our eyes? No, but we could see it with detectors. And you know what? Was it found? Did they find it?
For hydrogen.
For hydrogen?
Oh, yeah.
Yes. They found it. And they found other photons out here in the UV that were calculated based on this equation. So this equation fits not just the visible, but it also fits the UV. And when you get to big numbers here, we're out in the, or bigger numbers here, we're out in the infrared. And there are a whole bunch of lines in the infrared that were predicted by this equation. So this is just a mathematical equation. The mathematical equation is very successful. It described the entire spectrum, well, actually, the entire UV, visible, and infrared spectrum for the hydrogen atom. Not just the we only looked at a little bit of the visible. And so now we have the law. This is the law of the spectrum of the hydrogen atom, the Rydberg law, or Rydberg equation. So now what do we do? Is that it? No. That's not it. We start to try to think about we hypothesize. What does N mean? What is N? What is N?
Oh, yeah.
Yeah. Well, the first thing is, from the map, we know that delta E is going to equal the energy of the photon, because we're looking at n final minus n initial. This is minus r sub h, 1 over n final squared minus 1 over n initial squared. And so delta E is equal to E final minus E initial. Therefore, E final must be minus R sub H over N squared final, minus a minus R sub H over N squared initial. Therefore, the energy of the electron, and this is what we're going to call the allowed energy state for the electron, can be determined as minus R sub H over N. Which led to the hypothesis that, this is the hypothesis. The hypothesis is that only certain energies of the electron are allowed. Right? In other words, the electron in a hydrogen atom is quantized. Why is it quantized? So the hypothesis is that electron energies in a hydrogen atom are quantized. Meaning that allowed energies, forbidden energies. All other energies are forbidden. Well, that's not really a hypothesis, that's fact. This is a fact that there are a whole bunch of gaps here of forbidden energies, right? And so, what did this lead to? Well, somebody tried to understand this. And so the first hypothesis was that the electrons have orbits. So if we're looking at this, and this led to Bohr theory. Let's go. I'm going to skip the whole hypothesis business and go right to the theory. The Bohr theory was this. Each allowed energy, and so the first allowed energy is what we call E1. E1 is equal to minus R sub H over 1 squared. Right. That's allowed. The next allowed energy would correspond to a larger orbit. which we'll call E2. And so the second allowed energy is minus R sub H over 2 squared. And so we have these. So the next one would be E3. E3. E3 is going to have a higher energy, minus R sub H over 3 squared, which is 9. The highest allowed energy, I didn't talk about, I should have. The highest allowed energy is E infinity. And so E infinity is minus R sub H over infinity squared. The highest allowed energy, we can calculate this. What is it? It's 0. And so 0 is the highest. 0 corresponds to the highest possible energy for the electron, and then all the other energies are lower and negative. And so it's kind of weird. The top is 0. Usually we like to put the 0 at the bottom. And so normally we like to keep the lowest possible energy, this one, and call it 0, and then all energies higher and positive. For electrons, we're going to call the highest energy 0 and all the others lower and negative. Does that make sense? It's just kind of a numbering system. Okay, so this is the Bohr theory. Bohr theory said that this, and therefore Bohr theory said, is a orbit of 1.5 allowed? No, it's forbidden. That's a forbidden orbit. Because the electron cannot orbit there. Is an orbit of 0.5 allowed? No. And so one of the big questions for Bohr was, if you have a positive and a negative, aren't they going to come together? Aren't they going to, like for example, this electron's orbiting and eventually it's going to lose energy and then crash into the nucleus, like an old satellite. You know? No, so that's not allowed. Why is it not allowed? They don't repel, they attract.
With the proton or the electron?
Why isn't it allowed? It just isn't. You know, it just isn't allowed. Why can't the electron spiral into the nucleus? It can't. Why can't we have an orbit halfway between here? It can't. It can't. This is like, you know, this is like your child and your parent says, you can't do that, right? Why? You can't. You know, that's it. And so, you know what that's called? That's called a postulate. You just have to accept that. You accept that, and that's all you can do, because how can you prove it? Prove to me that 1.5 is not allowed. Well, I can prove it because it just doesn't fit the data. So you just got to accept it. Why isn't it allowed? Well, we don't care why it isn't allowed. We're just trying to describe nature, and this is nature. Nature says it's not allowed, therefore it's not allowed. Right? And so that's kind of a postulate, but is that a very satisfying way of understanding? No, and so we need a more detailed description. But we don't have to worry about that because Bohr ends up being wrong anyway, failing. So we don't want to spend much time on Bohr because it was wrong. All right, we'll stop here.